Review of the derivative and notation. Welcome to this session. Today, we are going to begin with a review of the derivative and the various notations associated with it. Starting with our first slide, it is important to recognize that in the study of calculus, the derivative is one of the most powerful tools available to us. It serves as the foundation for much of the advanced mathematics you will encounter. To understand what it actually does, we look at its core purpose. The derivative represents the instantaneous rate of change of a function with respect to its independent variable. While you may be familiar with average rates of change, the derivative allows us to zoom in on a single point to see exactly how the function is behaving at that precise location. In simpler terms, it tells us how fast a value is changing at a specific moment. As we move forward in this lesson, we will transition from this conceptual understanding to the formal mathematical definition, explore the different ways mathematicians write the derivative, and eventually apply these concepts to real-world examples, such as calculating the velocity of a moving car. The formal definition of the derivative. Now that we have established that the derivative represents the instantaneous rate of change, let's move on to slide 2, where we will examine the formal mathematical definition. Suppose we have a real-valued function, which we will call f, defined over a specific domain. Our objective is to find the exact rate of change of this function at one specific point, where x equals c. To do this, we need to compare the value of the function at point c with its value at a point that is shifted by a very small amount, which we denote as h. Therefore, we look at the function at the point c plus h. This brings us to the formal definition of the derivative. The derivative of f at point c, denoted as f prime of c, is defined as the limit as h approaches 0 of the quantity f of c plus h minus f of c, all divided by h. To make this formula easier to digest, let us break it down into 4 manageable steps. First, let's look at the numerator. f of c plus h minus f of c, this term represents the change in the output value of the function. In simpler terms, this is the rise that occurs as the input moves from c to c plus h. Second, we have the term h in the denominator. This represents the change in the input variable, which we can think of as the run. Third, when we combine these into the fraction, f of c plus h minus f of c, divided by h, we are calculating the average rate of change. Geometrically, this is equivalent to the slope of the secant line passing through the interval from c to c plus h. Finally, we apply the limit as h approaches 0. By doing this, we shrink the interval h until it becomes infinitesimally small. This critical step transforms the average rate of change into the instantaneous rate of change at the exact point c. Understanding this limit process is fundamental, as it allows us to move from a general average to a precise moment in time, which we will see applied in our upcoming examples. In the next slide, we will look at the various ways mathematicians write this concept using different notations. Notations of the derivative. Now that we have established the formal definition of the derivative using limits, let's discuss how we actually write it. In mathematics, you will encounter several different notations depending on the context of the problem you are solving. It is essential that you recognize these various symbols because, although they look different, they all represent the same fundamental concept, the instantaneous rate of change that we just defined. First, let's look at Lagrange's notation. This is very common in algebra and calculus textbooks and uses a prime symbol. If your function is f of x, the derivative is written as f prime of x. If you are evaluating the derivative at a specific point c, you simply write it as f prime of c. Next, we have Leibniz's notation. This is widely used in physics and engineering. If we define y as being equal to f of x, the derivative is written as di dx. This notation is particularly useful because it emphasizes that the derivative is the ratio of a small change in y to a small change in x, mirroring the rise-over-run concept we discussed in the previous slide. Then there is functional notation. The expression d dx of f of x represents the actual operation of differentiation being applied to the function f of x when we want to evaluate this operation at a specific point c. It is written as d dx of f of x, followed by a vertical bar with a subscript c. Finally, there is a simple shorthand notation. In some contexts, if the function is already represented by y, the derivative is simply written as y prime. While these notations allow us to identify the derivative at a specific point, in the next slide, we will see how to generalize this process to create a general derivative function. The general derivative function. Now, in the previous slide, we focused on how to find the derivative at one specific, fixed point, which we labeled as c. However, we can take this a step further and generalize the process. If we replace that constant c with a variable x, we are no longer just finding a single value. Instead, we obtain a brand new function called the derivative function, which we denote as f prime of x. This is defined as the limit as h approaches 0 of the fraction, f of x plus h minus f of x, all divided by h. This entire mathematical process of finding this general function, f prime of x, is known as differentiation. The advantage of finding this general derivative function is that we no longer have to perform the limit calculation for every single point. Once we have the derivative function, we can find the slope of the original function at any point in its domain simply by substituting the specific value of x into the formula. Real-world example, velocity. Now that we have established the formal definition and the various notations of the derivative, let us apply these concepts to a real-world scenario to see why they are so useful. A classic application of the derivative is the relationship between position and velocity. Imagine a car moving along a straight road. To describe this mathematically, let us define a function, s of t, which represents the position of the car at any given time, t. To understand how the derivative works here, let us break it down into a few steps. First, consider the average velocity. If we want to find the average velocity between a starting time, t, and a slightly later time, t plus h, we calculate the change in position divided by the change in time. In mathematical terms, this is the change in position, s of t plus h minus s of t, divided by h. You will notice that this is the exact same structure as the difference quotient we discussed in the formal definition on slide 2. However, average velocity doesn't tell us what is happening at a single moment. To find the instantaneous velocity, which is the exact speed shown on the car's speedometer at the precise moment t, we must apply the limit. By taking the limit as h approaches 0, we shrink the time interval until it is infinitesimally small. We denote this instantaneous velocity as v of t, which is the derivative of the position function, written as s prime of t. The formula is the limit as h approaches 0 of the quantity s of t plus h minus s of t, all divided by h. In conclusion, the derivative of the position function with respect to time is the velocity function. This demonstrates that the instantaneous rate of change we mentioned earlier is not just a theoretical concept, but a practical tool for measuring motion. Now, while this application seems intuitive, there are some common algebraic traps students fall into when calculating these limits, which we will cover in the next slide. Common mistakes to avoid. Now that we have seen how the derivative applies to real-world scenarios like velocity, it is crucial to address some common pitfalls to ensure your calculations are accurate. First, let's discuss a frequent algebraic error. Confusing f of x plus h with f of x plus f of h, it is a common misconception to assume that these two expressions are equal, but in almost all cases, this is false. When you are applying the definition of a derivative, remember that you must substitute the entire expression, x plus h, into the function wherever the variable x appears, rather than simply adding two separate functions together. Secondly, be mindful not to ignore the limit. As we discussed back in the formal definition, calculating the difference quotient, which is f of x plus h minus f of x, all divided by h, is only the first step of the process. If you forget to apply the limit as h approaches 0, you are merely finding the average rate of change over an interval, which is the slope of a secant line, rather than the instantaneous rate of change, which is the actual derivative. Finally, let's address notation confusion. While Leibniz's notation, written as dy over dx, looks like a fraction, it is important not to treat it as a simple fraction during complex operations. Always keep in mind that this symbol is a shorthand representation of a limit process, not a division of two independent variables. Keeping these warnings in mind will help you avoid common errors as we move into our final summary of the key takeaways. Key takeaways. To wrap up our session, let us review the key takeaways from this lesson to ensure you have a solid foundation before we move forward. First, always remember that the derivative represents the instantaneous rate of change of a function. As we discussed in our opening and illustrated with the velocity of a car, it tells us exactly how fast a value is changing at one specific moment in time, rather than over an interval. Secondly, we have the formal definition, which is based on the limit of the difference quotient. In mathematical terms, this is expressed as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. This formula is the heart of calculus, as it allows us to shrink the distance between 2 points until they essentially become one. Third, please be mindful of the different notations we covered. Whether you encounter f prime of x, dy dx, or the derivative of f of x with respect to x, remember that these are simply different ways of writing the same concept depending on whether you are in a pure math, physics, or engineering context. Fourth, keep in mind that the actual mathematical process we use to find this derivative function is called differentiation. This is the step that allows us to move from calculating the slope at a single point to finding a general formula that works for any point along the function. Finally, from a geometric perspective, the derivative at a specific point is the slope of the tangent line to the curve at that point. If you imagine a line just barely touching the curve at one single spot, the derivative gives you the exact steepness of that line.